This presentation gives an introduction to digital twinning. It can be used in different courses because it's an important subject, not only in the water area but in the engineering environment at large and even outside engineering. It starts by a question: what is a digital twin and how does it work? Then the difference between digital twinning and simulation, and the type of digital twins, history of digital twin technology, and the project industry, market and applications, and a few slides on the future of digital twins, and a concluding remark. A digital twin is a virtual representation of an object or system designed to reflect a physical object accurately. It spans the object's life cycle, is updated from real-time data, and uses simulation, machine learning, and reasoning to help make decisions. In this presentation, I added a lot of infographics to explain the idea. And in this infographic, it's about what is a digital twin. The real world is reproduced as a virtual world and a computer based on the collected data, and it shows you the virtual simulations are fed back into the real world. Another infographic about the three elements of a digital twin: the real world entity or process, the data that connects the two, and the virtual representation. How much fidelity equals a digital twin? This group of slides talks about more deep definition of what is a digital twin. Fidelity in this context is the degree of exactness between the digital representation and the real world. We have three dimensions of fidelity we must consider: looks alike, behaves like, and connected to. The following two infographics, for example, a photo is a perfectly accurate look-alike representation of the real world, but has no fidelity in terms of behaves alike, since it is just a two-dimensional image. There is quite some debate as to how much fidelity is required before we can use the moniker digital twin. On one hand, if we call a 2D photo a digital twin, we run the risk of making the term meaningless. Alternatively, if we hold out for a fully immersive one-to-one accurate simulation, we may never realize any benefits at all. We look at this graph. It shows the y-axis as looks alike fidelity, and x-axis behaves like fidelity, and of course we like photo is high on the y-axis, and behaves like we have a two-dimensional drawing and an Excel model with some calculations, and in the middle you can find photogrammetry, point cloud, BIM model, finite element analysis, and discrete event simulation. The other graph, the y-axis changes to connected to fidelity, where we have high in the y-axis two-way control and dynamic control, followed by real-time SCADA and Internet of Things, and historical SCADA, Internet of Things. On the x-axis we have the Excel model and the finite element analysis. Looking at the connected to fidelity continuum is more to do with the degree to which a digital twin is plumbed into the real world. So there we have it. A digital twin is a highly fidelity representation of a real world that looks like, behaves like, and is connected to the real world, the purpose of which is to improve understanding and decision making. How does a digital twin work? We are using an example here of a wind turbine. It is fitted with various sensors related to vital areas of functionality. These sensors produce data about different aspects of the physical object's performance, such as energy output, temperature, weather conditions, and more. The processing system receives this information and actively applies it to the digital copy. How does a digital twin work? After being provided with the relevant data, the digital model can be utilized to conduct various simulations, analyze performance problems, and create potential enhancements. The ultimate objective is to obtain valuable knowledge that can be used to improve the original physical entity. Here is another infographic that shows the three elements: the digital model, the digital shadow, and the digital twin. And the dotted line is for manual data flow, and the blue continuous line is the automatic data flow between physical object and digital object. Here we differentiate between digital twins and simulations. Although simulations and digital twins both utilize digital tools to replicate a system's various processes, a digital twin is actually a virtual environment, which makes it considerably richer for study. The difference between a digital twin and simulation is largely a matter of scale. While a simulation typically studies one particular process, a digital twin can run any number of useful simulations to study multiple processes. The differences don't end there. Simulations usually don't benefit from having real-time data, but digital twins are designed around a two-way flow of information that occurs when object sensors provide relevant data to the system processor, and then happens again when insights created by the processor are shared back with the digital source object. By having better and constantly updated data related to a wide range of areas, combined with the added computing power that accompanies a virtual environment, digital twins can study more issues from far more vantage points than standard simulations can, with greater ultimate potential to improve products and processes. There are different types of digital twins, and I'm going to show a series of beautiful infographs. The types are depending on the level of product magnification. The biggest difference between these twins is the area of application. It is common to have different types of digital twins coexist within a system or process. Let us go through the types of digital twins to learn the differences and how they are applied. Here we have four categories: component, asset, system or unit, and process. They are all twins. Types of digital twins: component twins or part twins are the basic unit of a digital twin, the smallest example of a functioning component. Parts twins are roughly the same thing, but pertain to components of slightly less importance. Asset twins, which is the second type, when two or more components work together, they form what is known as an asset. Asset twins let you study the interaction of those components, create a wealth of performance data that can be processed and then turned into actionable insights. This is an infographic showing the relation between physical world, digital world, and conceptual world, where in the asset to the left you can find observe, build, and operate, and in the idea side you can have design, plan, and assess. Types of digital twins we have system or unit twins. The next level of magnification involves systems of unit twins, which enable you to see how different assets come together to form an entire functioning system. System units provide visibility regarding the interaction of assets and may suggest performance enhancements. Process twins, the macro level of magnification, reveal how systems work together to create an entire production facility. Are those systems all synchronized to operate at peak efficiency, or will delays in one system affect others? Process units can help determine the precise twinning schemes that ultimately influence overall effectiveness. Here you can find a physical asset and sharing information with the digital twin for component or part asset. And here is a twin system where we have hardware, we have middleware, and we have software. Middleware includes data storage, data processing, and data modeling. You can find sensors and actuators on the hardware side, and simulation environment and analytics on the software sides. And it's a two-way exchange, as we mentioned before. Here is another example of digital twin system from the medical environment, showing the physical and virtual parts. For the physical, we have extensive monitoring via sensors, and in the virtual we have computer models, and we use a clinical decision support system by either clinicians or by autonomous or algorithmic decision-making system, and these actuators are applied to the patient, as you can see. Here is a more elaborate example of a process. Understanding the role of digital twin in modern manufacturing, you can find a lot of elements and a lot of assets inside. History of digital twin technology. The idea of digital twin technology was first voiced in 1991 with the publication of a beautiful book called Mirror Worlds by David Gellertner. However, Dr. Michael Greaves, then faculty at the University of Michigan, is credited with first applying the concept of digital twins to manufacturing in 2002 and formally announcing the digital twin software concept. Eventually, NASA's John Vickers produced the new term digital twin in 2010. It starts in 1991 and the expression is coined in 2010. This is the front page of the book, and I like to read the subtitle: Mirror Worlds, or the day software puts the universe in a shoebox. How it will happen and what it will mean, by David Gelernter. History of digital twin technology. However, the core idea of using a digital twin as a means of studying a physical object can actually be witnessed much earlier. In fact, it can be rightly said that NASA pioneered the use of digital twin technology during its space exploration missions in the 1960s, when each voyaging spacecraft was exactly replicated in an Earth-bound version that was used for study and simulation purposes by NASA personnel serving on flight crews. Here it goes deeper in history and relates the application of the idea not to the 1991 but to the 1960s. Advantages and benefits of digital twins: better R&D, research and development. The use of digital twins enables more effective research and design of products. with an abundance of data created about likely performance outcomes. Greater efficiency. Even after a new product has gone into production, digital twins can help mirror and monitor production systems with an eye to achieving and maintaining peak efficiency throughout the entire manufacturing process. Product end life. Digital twins can even help manufacturers decide what to do with product that reach the end of their product life cycle and need to receive final processing through recycling or other measures. Also, digital twin market and industries. While digital twins are prized for what they offer, their use isn't warranted for every manufacturer or every product created. Not every object is complex enough to need the intense and regular flow of sensor data that digital twins require. Nor is it worth it from a financial standpoint to invest significant resources in the creation of a digital twin. Projects benefiting from digital twins. We have physically large projects in areas of buildings, bridges, and other complex structures. Mechanically complex projects like jet turbines, automobiles, and aircraft. Power equipment. It includes both the mechanisms of generating power and transmitting it. Manufacturing projects. Digital twins excel at helping streamline process efficiency, as you would find in industrial environments with co-functioning machine systems. I'm going to show a series of beautiful infographics. This is digital twin technology in construction. This is infrastructure digital twin technology. We have the physical twin and the digital twin and information and decision. This is a digital twin assisted AI for sustainable RAN. RAN stands for Radio Access Network. Is a part of a mobile network that connects end user devices like smartphones to the cloud. Here is digital twins in manufacturing. You can find the complexity of the process here. Industries with large scale products includes engineering systems, automobile manufacturing, aircraft production, rail car design, building construction, manufacturing, and power utilities. I'm going to use another set of beautiful infographics. This is the digital twins in systems engineering. Digital twin arrangement applied to automotive industry. This is General Electric created a digital twin for fan blades for its most popular GE90 engine that surpassed the 100 million flight hours. And this is digital transformation in rail asset management with Delmia to enhance efficiency and sustainability. The integration of digital twins and BIM in construction projects, and this is digital twin for manufacturing and digital twins applied to power grids. Digital twin market poised to grow for growth. The rapidly expanding digital twins market indicates that while digital twins are already in use across many industries, the demand for digital twins will continue to escalate for some time. In 2022, the global digital twins market was projected to reach $73.5 billion US dollars by 2027, as we can see in this graph here. Digital twin market, the global level. Improving manufacturing efficiency with digital twin. The use of end-to-end digital twin lets owners and operators reduce equipment downtime while upping production. Discover a service lifecycle management solution created by IBM and Siemens. Digital twin applications. This is some kind of repetition of what we have mentioned before. These applications include power generation equipment, structures and their systems, manufacturing operations, healthcare services, automotive industry, and urban planning. The future of digital twin. A fundamental change to existing operations models is happening. A digital reinvention is occurring in asset-intensive industries that are changing operating models in a disruptive way, requiring an integrated physical plus digital view of assets, equipment, facilities, and processes. Digital twins are a vital part of that realignment. The future of digital twins is nearly limitless because increasing amounts of cognitive power and constantly being devoted to their use. So, digital twins are constantly learning new skills and capabilities, which means they can continue to generate the insights needed to make products better and processes more efficient. Here is my last slide, and it shows you how digital twins is connected to almost everything in our daily life. Here we can say connected city, connected grid, connected building, connected vehicle, connected factory, connected highway, and we have social environment and the economy atmosphere, and you can see these little circles here. It's about factory optimization, logistics optimization, and traffic sensors and cameras, automated car systems, and how they are connected to digital twins. Concluding remarks. Digital twins serve as advanced virtual replicas of physical objects or systems, utilizing real-time data and simulations to enhance decision making and improve performance throughout the object's life cycle. Their growing applications across various industries highlights their potential to drive efficiency, innovation, and inform product development.